These are some of the newest, most fuel-efficient airliners ever built. Right now, 720 of them cannot fly. Not because of a crash, not because of a design flaw, because of contaminated metal powder. This grounding represents 38% of all A320Neo family aircraft powered by the Pratt Whitney PW1100G. Out of 1,912 operational jets with this engine, 720 are idle. By late October 2025, the total number of grounded geared turbofan aircraft reached 835 worldwide, an increase of 90 jets since summer. Yet, this is not an aircraft design failure. Operators of the same Airbus airframe powered by the alternative CFM LEAP-1A engine experience a normal 4% grounding rate. Related engines on the Airbus A320 and Embraer E2 also remain mostly active. The crisis is isolated to a single supply chain. The engineering failure lies within the engine's hot section, specifically inside the high-pressure turbine and compressor discs that hold the blades in place. Between 2015 and 2021, the nickel-based alloy powder used as the raw material to forge these rotating parts was contaminated with microscopic impurities. During normal flight, these discs experience extreme heat and centrifugal force. The microscopic contaminant particles act as stress concentration points, nucleating tiny cracks that grow slightly larger with every takeoff and landing. To prevent catastrophic failure, regulators ordered an inspection campaign to identify and replace suspect components, though engineering data does not suggest that every contaminated disc will fail. This metallurgical defect is entirely separate from the geared turbofan design itself. The engine's gearbox, which allows the main fan and the internal turbine to spin at different optimal speeds, works exactly as designed. This mechanical architecture is the precise reason airlines selected the engine, as it delivers a 16% reduction in fuel burn and a 50% decrease in noise compared to previous generation narrow-body aircraft. The basic technology achieved its design goals. The crisis is entirely a consequence of a manufacturing defect during that 6-year production window. On March 18, 2020, an IAE V2500 engine on a Vietnam Airlines jet suffered an uncontained high-pressure turbine disc failure. Pratt Whitney, the majority owner of the International Aero Engines program, traced the crack directly to contaminated powder metal from its New York facility. The FAA issued an emergency directive, eventually ordering target PW1100G disc replacements in September 2021. Yet, public disclosure did not arrive until July 2023, initially targeting 1,200 engines. By September, the scope expanded to 3,000 engines, requiring off-wing shop visits, triggering a $3 billion RTX pre-tax charge. Active legal filings allege company leaders knew of the defect years before warning operators. While corporate accountability and timeline awareness remain highly contested, the immediate industrial challenge is finding the physical maintenance capacity to rebuild them. The physical reality of this recall collided immediately with a severely constrained global maintenance network. Under normal operating conditions, a standard PW1100G engine overhaul requires 60 to 90 days. Under the weight of the recall, that turnaround time ballooned to between 250 and 300 days. Every engine requires dismantling, ultrasonic inspection, machining, and certification, creating a massive queue that exceeds available labor and shop slots. MTU Aero Engines, which holds an 18% stake in the program, projects a €1 billion revenue hit from these delays. To alleviate the pressure, Pratt Whitney certified additional overhaul facilities at Iberia, China Airlines, and Korean Air. But expanding shop space does not solve the underlying parts shortage. Forging capacity remains distinct from overhaul capacity. A new isothermal forging press in Columbus, Georgia, will not go online until 2028, when it is expected to raise critical component output by 30%. Until then, almost all newly forged turbine discs must be diverted directly to emergency repairs, starving the new aircraft assembly lines as the backlog grows. Spirit Airlines operated an all-Airbus fleet of 207 aircraft in the middle of 2024. The majority were A320Neo family jets powered exclusively by geared turbofans. This extreme fleet concentration offered operational simplicity and stable times, but left the carrier completely exposed during a systemic engine shortage. Spirit could not substitute other engine types to keep flights running. By the end of 2024, approximately 40 of its jets sat idle. By July 2025, 39 A320Neos were grounded, leaving just 52 in service. The missing capacity cut deep into flight schedules, hammered aircraft utilization, and reduced revenue, while fixed lease obligations remained due. In November 2024, Spirit filed for Chapter 11 protection. The initial restructuring plan capped the future fleet at 106 aircraft. But the engine crisis, combined with intense liquidity pressure, rising fuel costs, and broader debt burdens, proved insurmountable. On May 2, 2026, Spirit commenced an orderly wind-down of operations, permanently halting all flights. The groundings had exposed the high risk of a single-engine fleet strategy. In 2026, Swiss International Airlines grounded its entire 9-aircraft A220-100 fleet. The carrier conserved these usable parts solely to keep its larger A220-300 fleet flying. Further south, ITA Airways faced prolonged groundings, leaving several aircraft idle in Naples for over a year. The airline prepared legal action to seek 150 million euros in damages from Pratt Whitney. For crews, the lack of active airframes choked career progression. At Wizz Air, Lufthansa Group, and Indigo, cadet pilots entered extended holding pools, unpaid holding patterns where qualified pilots sat with no aircraft to fly. This stagnation drained cash from lessors, reduced airport activity, and cut hours for ground crews, intensifying pressure for a fix that improves both on-wing durability and maintenance throughput. Pratt Whitney developed the GTF Advantage durability package to resolve the failure path directly. The Federal Aviation Administration certified this updated engine design, designated the PW1100G-2JM in February 2025. The European Union Aviation Safety Agency followed with its own certification on April 17, 2026. To upgrade the existing fleet, the manufacturer introduced the Hot Section Plus retrofit, allowing operators to install revised, more durable turbine components during scheduled shop visits, instead of switching to a new engine variant. Pratt & Whitney claims this upgrade provides up to double the time on wing and up to 8% additional thrust. However, regulatory approval proves design compliance, not long-term operational reliability. A complete production cutover to the new standard is delayed until 2028. This leaves airlines waiting for a physical solution that their grounded fleets require immediately, exposing a persistent mismatch between certification and industrial capacity. In January 2026, leasing giant Aviation projected that more than 150 geared turbofan aircraft would return to service during the year. But these returns represent a slow draining of the backlog, not a sudden end to the crisis. Analysts expect engine-related disruptions to persist well into 2027, as overextended maintenance shops struggle to clear the queue. For airlines and lessors, the grounded fleet represents billions of dollars in idle capital, compounding lost lease income, and forcing the search for expensive replacement capacity. This crisis reveals how a single manufacturing process can propagate risk through an entire aircraft generation. Operators who chose the alternative CFM LEAP engine avoided these groundings, proving that fleet selection distributes risk as well as performance. Ultimately, recovery depends on a delicate industrial balance. MRO expansion, clean parts, and retrofits must arrive faster than new engine removals. Whether sustained aircraft returns can outpace incoming defects through 2027 remains the defining question for the global aviation supply chain. Subscribe for more aviation and industrial supply chain investigations. Today, the aviation industry faces an unforgiving bottleneck. As airlines wait until 2027 for physical fixes, this crisis reveals a deeper systemic truth. In the relentless pursuit of efficiency, the margin for industrial error has shrunk to zero.